Recently, I was doing differential equations, ODEs, and how we solve a particularly well-behaved class of them. And the way we do that is we replace nth derivatives with x raised to n to give us what we call the characteristic equation, and we use the roots and take their exponential functions and yada yada yada. My mind was already thinking on a different track. The characteristic equation. It seemed vaguely familiar, and I thought, do I know you? I feel like I know you. And I did know it. At least a form of it. In recurrence relations. In fact, the way we solve recurrence relations, again a special class of them, is almost identical to how we solve these particular ODEs. These well-behaved ODEs I'm referring to are called linear homogeneous differential equations, and these recurrence relations are, unsurprisingly, linear homogeneous recurrence relations. And as if that wasn't enough to warrant my search for a deeper connection, another place the characteristic equation comes up is with matrices, linear transformation. After all, what is math? Henri Poincaré said it best. Let's first understand the most apparent link. What does it mean for an equation to be linear and homogeneous? Arguably, the most famous of such recurrence relations is that of the Fibonacci sequence, whose terms are recursively defined by an is equal to an minus 1 plus an minus 2. It is said to be homogeneous because each term, that is the ai's, have the same degree, namely 1. That is to say, we don't have an ai times aj or an ai cube or an n or something like that. And linear means that the highest degree is 1. Basically, all this means is we have a bunch of ai's multiplied by a bunch of constants with plus or minus signs in between. More generally, this is what such a recurrence relation looks like. How does all this help us? Well, because it is homogeneous, if we multiply each ai by some constant c, we can just factor out its power. So, if an explicitly defined function f of n gives us a sub n, that is, it satisfies this equation, then so does c times f of n. Also, because of linearity, if we add two functions, say f of n plus g of n, for a sub n, they can just be separated out into their own expressions. So if two functions, f of n and g of n, satisfy our equation, then so does their sum, f plus g of n. Isn't that neat? If you give me a bunch of particular solutions, I can tell you that their linear combinations, that is, multiplied by a bunch of constants and added together, will all be solutions as well. Now, let's look at some simpler recurrence relations to get hints for what our particular solutions might look like. In this example, we can see that an, which is k times an minus 1, is equal to k squared times an minus 2, which is equal to k cubed times an minus 3, and on up till k raised to n times a naught, giving us an to be a naught times k raised to n. Let's now go back to the Fibonacci sequence. Its explicit formula is famously called Binet's formula. And that looks a little messy, so let's clear some of the clutter and focus on a basic form of it. These look very similar. We have constants and we have constants raised to n. In fact, it is very reasonable to claim that our recurrence relations have solutions of this form, x raised to n. And that is more or less how we solve these recurrence relations. Let's go through an example. We let x raised to n as an be a solution and proceed to find x, which will be a root of the characteristic equation. So we combine the exponents linearly to find our general solution. Moving on to ODEs. Once again, the homogeneous nature lets us factor out c, since the derivative function is nice enough to let us. And once again, the linear nature lets us separate the expressions in f and in g, since the derivative function has a nice additive property. And once again, the particular solutions combine linearly to give the general solution. And checking out a basic ODE hints at exponential functions being good particular solutions. So, to solve these, we assume e to the ax to be a particular solution, which again brings us to the characteristic equation, leading us to the general solution. And that's all well and good, but it kinda left me with the feeling, yeah, sure, they look the same, they solve the same way, why not? Big deal. And yeah, it's not that big a deal. In fact, we can easily convert ODEs into recurrence relations. All we need to do is realize that differentiating the ODE simply shifts the derivatives, so it seems natural to set the sequence of derivatives as our sequence of AIs. For example, but we already know the solution for this sequence, so we can use this result, noting that C1 and C2 are constants with respect to n and not x, so we must let them be functions f and g of x. And we use the condition that each successive term of this sequence is the derivative of the previous one, and compare the equations to get f and g, and ultimately y. The connection between the characteristic equation of matrices and that of recurrence relations and ODEs is not so obvious, but it becomes apparent when we recall what eigenstuff actually mean. The eigenvectors of a transformation matrix M are the vectors that do not get rotated under M, only stretched or squished, possibly by a negative number. Notationally, this is what it means, where V is the eigenvector and lambda, its scaling factor, is called its eigenvalue. Now we use the identity matrix to get the RHS in the matrix times vector form as well, and for this equation to have a non-zero vector solution, we need the determinant to be 0, and this is called the characteristic polynomial. Its roots are the eigenvalues, which allow us to find the eigenvectors. So, if we were to repeatedly multiply V by the matrix M n times, we would simply have lambda raised to n times V, which is pretty neat, because usually repeated matrix multiplication tends to get really messy really fast. As a result, if our vectors were represented as a linear combination of these eigenvectors instead of the usual 1, 0 and 0, 1, repeated matrix multiplication would no longer be as troublesome. But hold on, that seems awfully familiar. Constants raised to n. Alright, let's try to use matrices to solve recurrence relations now. So here's our recurrence relation. Now an can be expressed as a linear combination of the previous terms, which makes it look an awful lot like a dot product. This hints at a way of mapping the column vector an-2 an-1 to the next an-1 an. And since we're working with vectors, we should look for a matrix that does this. Our previous dot product gives us one of its rows, and the other one is not tricky to find either. Now applying this transformation n times on a0 a1 will give us an plus 1. And how do we find m raised to n? Eigenbases, of course. So first we find the eigenvalues by setting the determinant equal to 0, giving us this equation, which I'm sure you must recognize as the characteristic equation of the recurrence relation, and surely the characteristic polynomial of the matrix. It is of course no coincidence that its coefficients are just those of a recurrence relation. This is also easy to see thanks to some properties and good old 0 and 1. Solving the equation gives 4 and minus 1 as our eigenvalues, using which we can get the eigenvectors. The 0 and 1 make them simply 1 lambda. Now we throw them together for the change of basis matrix. So the transformation M in this basis will be B inverse of M of B, which is this stuff. But we need not go through all this to find M sub B. We can simply go back to why we're doing all this in the first place and what eigenstuff actually mean. Under M, the eigenvectors simply get scaled by their eigenvalues. So if we start expressing vectors as linear combinations of these vectors, then their components will simply get scaled by the eigenvalues, making repeated matrix multiplication exponentially cleaner. Converting back to our original basis gives m raised to n to be b of m sub b of b inverse, which is simply this stuff. So we get an. And we can make this nicer by sweeping up all the messy stuff and calling them simply a bunch of constants, which depend upon the initial conditions, of course. So now we know of a way to connect recurrence relations with matrices. Now let's go ahead and connect ODEs with recurrence relations, the well-behaved ones, of course. Let's rewrite the ODE purely in terms of y. For the recurrence relation, we'll first shift it to get an at the far right, similar to where y was, and represent it similarly. Here f is the function taking one term to its next, that is an to an plus 1, an plus 1 to an plus 2, and on and on. So both our ODE and recurrence relation are basically of this form: a function f and a function g composed with itself several times and acting on f. Let's systematically compare their similarities. H is, in both cases, homogeneous and linear. The reason for which is mainly because g, the derivative function in the case of ODEs, has these nice properties. For recurrence relations, f, the shift function, does the same. More pedantically, f and d are both linear transformations. So would it be right to call them matrices? Does that make the series an and the function y vectors? Sure, why not? To represent these vectors in a form we're already familiar with, an can simply be the list of its terms. Accordingly, the shift function f can be the matrix sending a0, a1 and so on to a1, a2 and so on. As a result, it will have 1s down this offset diagonal and minus bi's in its bottom row. Generally, vectors can all be thought of as linear combinations of more basic, already recognized vectors called the basis vectors. Recognizing what possible bases are can be key in deducing the vector forms of vector-like stuff. Take polynomials, for example. It feels natural to break them up into terms according to their degrees. So, a polynomial as a vector can be simply the list of its coefficients, making the derivative function this good-looking matrix, thanks to the power rule. Let me introduce some terminology at this point. All these vectorish things, sequences, polynomials, arrows in space, pairs of points, complex numbers, these are all different vector spaces. Their elements satisfy some nice properties, which lets us use the same concepts on all of them, without having to come up with different theories for all these seemingly different vector spaces. For all of them, we can define vector addition, dot product, scalar multiplication, eigenstuff, which are, we all know, pretty useful. Let's try to explore what some of these properties, fondly called axioms, should be. Starting with vector addition. Through some examples, it's easy to see that components simply seem to add to each other, so the order of addition doesn't seem to matter. Even looking at vectors as arrows, we can see that the resultant of u plus v is the same as that of v plus u. The parallelogram is a nice visualization of this. More generally, Adding vectors comes down to adding the individual components and the normal addition of reals, which is very well known to be commutative and associative. The commutativity and associativity of vector addition are two of the aforementioned axioms. Now I want to pull you back to some eigenstuff. Remember how we came to the characteristic polynomial? Well, there's a step here that we unconsciously skip over. Firstly, the reason we do all this is because the zero vector is particularly nice. It is the unique vector that on adding to something else doesn't change that something else. Due to this property, we fancifully call it the additive identity of vector addition. And the pair of vectors that add together to give us this zero vector are called additive inverses of each other, and these two are unique. This is their general definition. Apart from adding together vectors, we can also multiply them by scalars or scale them, and this scalar multiplication plays very nicely with field multiplication, which is multiplying scalars together. For example, scaling a vector by 2 and scaling the resultant by 3 is the same as directly scaling the original vector by 6. And it works similarly for functions. This is called the compatibility of scalar multiplication with field multiplication. And the way we have the identity matrix that takes a vector v to itself, we also have the identity element of scalar multiplication that scales v to itself. Also note that adding two vectors and then scaling them by, say, 2 is the same as first scaling them by 2 and then adding. The scalar gets distributed over the individual summands. This is called the distributivity of scalar multiplication over vector addition. Analogous to this is that adding twice of the vector to thrice of it is the same as scaling the original vector by 5. The vector gets distributed. This is called the distributivity of scalar multiplication over field addition. And these were the 8 axioms of abstract vector spaces. I, for one, find it really amazing to find such connections all over math. After all, what are coincidences anyways?